This is Introduction to Exercise 16E on the normal application to binomial distribution. When we use binomial distributions, now before we've seen them in the form of histogram, seen them in the form of having dots and then dotted lines all the way down to the x-axis. But what we can do is that if we have a decently large size sample, we can approximate a normal distribution on top of the binomial distribution to make our life a little bit easier. If you look in this first row, you'll see n representing the sample size and p representing the probability. And then you'll see, based on those two values, for our binomial distribution, what does that look like? If n equals 10, we're keeping our n as a sample size of 10 across the first row, and we're changing the probability from low to high, so 0.2, 0.5, 0.8. Of course, it makes sense that if our probability is at 0.2, a lot of our data is skewed towards the negative side. Whereas if it's a 0.8 probability, it's more skewed towards the positive side, or it's negatively skewed. However, if it's probability of 0.5 dead center, you end up with a binomial distribution that's quite symmetrical around the center. In the second row, we're increasing the value of our sample size, but we're keeping the same probabilities. And you'll see that even though you can still note a slight skew, it's getting less asymmetrical than before. And by the time that we increase our sample size to 50, you already see a very slight difference in terms of its symmetrical nature. As we get to 100, they pretty much just look like normal distributions. So, looking at this, we can tell that the average, as the sample size increases, if it's a large sample size and is a big number, and also if the probability is closer to 0.5, we can start approximating a normal distribution. Of course, that means when n is large, or p is close to 0.5, we'll end up with a very similar normal distribution, and in such cases we can replace that binomial distribution with a normal distribution. Now, it's not always going to be perfect, of course. Just like when we're extrapolating versus interpolating data, we might end up with some slightly different answers. So for example, the one we looked at in the last lesson was about how even though you can't have negative lengths of metal rods or negative time taken to complete a certain task, we still go from negative infinity to whatever value because we're replacing with a normal distribution. We can use the mean and standard deviation of the distribution in a very unusual way, or in the usual way, and we can replace it with NP for our mean, which is something that we already addressed in the previous lesson. And of course, our standard deviation, which is the square root of NP bracket 1 minus P, remembering that when we square root, of course, standard deviation equals the square root of variance, which is where we got that formula from. Generally speaking, if we want to find whether we can mathematically determine something can be appropriately replaced with a normal distribution, we want to say that generally NP and n bracket 1 minus P should be greater than 5 for a satisfactory approximation. Any questions? Okay. So if you get you multiply NP, or you go n times 1 minus P, end up with a value of 20 or 30 or whatever, generally speaking, we can use a normal approximation. If you multiply those and get less than 5, we try not to use a normal approximation. Let's look at the example below. A sample 1,000 people from a certain city were asked to indicate whether or not they were in favor of construction of a new freeway. It is known that 30% of people in the city are in favor of the new freeway. Quick, Zach, give me some information that's important here. Good. Sample size of 1,000 people. What else? Keely, give me something else.
30%
Perfect. 30% of people in favor. We need to find the approximate probability. Note approximate because there are a few ways of doing this. Between 270 and 330 people in favor. Okay, a lot of information. But what we can do is we can try to apply this using binomial distribution. But we can also apply understanding of normal distribution. Note that for the textbook questions, it does say to assume to use normal distribution. Just give you a heads up. Let's determine the values. But before we do that, let's define what we're looking for. So let's let x equal to the number of people in sample. Oops. In the sample in favor. So very simple, we're just defining the value of x is the number of people in the sample in favor. Let's assume binomial random variable. The n equals to 1000 and p equals to 0.3. Of course, based off the 1000 sample size and the 30% of people in favor. Now, let's just double check. Generally speaking, it should be pretty obvious, but let's just double check whether or not we should use a normal distribution. It says NP, let's start with NP. N times P gives me 1000 times by 0.3 gives 300. That's massively greater than 5, perfect. N times 1 minus P, which would be 1000 times by 0.7, 700. Great, that's perfect. They're both massively over 5, therefore normal distribution will be pretty satisfactory. Let's find the value of mu. Mu, of course, referring to my formulas above, is n times p. We already know that from a previous exercise. There we go. Where n times p gives us 300. And our standard deviation equals to the square root of n times by p, which is 1000. Let's try that again. 1000 multiplied by 0.3, and we're multiplying that again by our 1 minus probability, which is 0.7. Which gives me an answer of, I'm going to keep it in exact values, of square root of 210. Now let's approach it using normal distribution. With that in mind, I can now say that the probability of x being between 270 and 330 is about the same. It's about the same as the probability, and I'm going to change it into my standard normal distribution by applying the formula from the last one, which is z equals to x minus mu over standard deviation. So 270, you know, I might need a little bit more space, so I'll just write that on the left-hand side. So it's approximately, and keep note of the approximately, being between 270 minus 300 over root 210, so I'm substituting my average and my standard deviation, less than, and I'm not writing x now because I'm using the standard normal distribution, so we're using z now, and we've got the same thing on the right hand side, 330 minus 300 over square root of 210. We can then put that into our calculator. We can go interactive, distribution, continuous, normal CDF. Going from, you'll put in your values, so 270 minus 300 over square root of 210, etc. I'm going to skip that step because I'm sure you guys put that in the calculator yourself. And you end up with approximately 0.9616. We would leave the standard deviation as 1 and our average is 0 because we're using the standard normal distribution when we use z. Alternatively, you could also just straight up use our values in this section here and put in our calculator where our lower bound is 270, our upper bound is 330, our standard deviation is the root of 210 as we calculated earlier, and of course our average is 300. And you get a slightly different answer. But it still works. It depends on what information you're given. Let's try to use our binomial distribution. So we'll go to interactive, distribution, discrete binomial CDF. Again, I'm going to put in 270 to 330. Our number of trials is 1000. And our probability of success is 0.3. And you'll again end up with a slightly different answer, but very similar. So 0.96475 as opposed to 0.961566. Very similar, but they're slightly different because again we're approximating. Okay? So the key skill, can you identify whether something can be approximated using the normal distribution? Can you calculate your sample based on your sample size, your average, your standard deviation, and apply a normal distribution approximation over the binomial distribution, and then calculate probabilities based on that? Any questions? Okay.